so I'm going to focus on Lab 3 today, which focused on circuits. And so the purpose of this lab was to understand how charge and energy are conserved in circuits and how we can observe that through current and voltage measurements. So I used two 1.5 volt battery setup with two resistors, 47 ohms and 100 ohms in series, and I found that the conventional current to be around 0.02 amps, and for RC circuits I used a 9 volt battery, 10 and 20 ohm light bulbs, and 0.2 farad capacitor. And so just a brief preview of my results show that the resistance affects how long it takes a capacitor to charge or discharge, and also calculated the time to be around 4.85 seconds. And so these were some of the principles I utilized. So I used Ohm's law, which just states that the current through a conductor is directly proportional to the voltage across its ends, and this is given that the resistance remains constant. I used the node rule, which states that the total current entering a node has to equal the total current leaving it, and the loop rule, which follows the conservation of energy, where basically it states that the sum of electric potential differences around any closed loop has to equal 0. And I also use capacitance, which is the idea that capacity of an object to store electrical charge, and linearization, which I will elaborate on further later. So the first circuit here included two 1.5 batteries and two ammeters and two resistors. Again, 47 and 100 ohms. We observed the current of 0.025 amps or 0.02 amps, and when I reversed the ammeter, it showed negative 0.02 amps, which just confirmed the direction of it. And so when we replaced one ammeter with voltmeter, and as expected, the current dropped to 0 amps while the voltage read 3 volts, which makes sense given the batteries' combined potential differences. And so moving on to the next part. Next, I examined the charge and current conservation series in the circuit and measured the potential differences at different points and created a potential versus difference graph as shown here to the right. And so when I added up the potential differences in the loop, they summed up to be 0 volts, which just confirms loop rule and demonstrates that the energy is conserved throughout a closed loop in the circuit. And these were the points that I measured in the circuit. And so in a different configuration, I placed the ammeter around the 100 ohm resistor, and since the ammeter has very, very low resistance, nearly all the current passed through it. And this effectively created a short circuit, so I used Ohm's law, which I just divided 3 volts by 47 ohms and estimated the current to be around 0.06 amps. And these values I calculated were slightly higher than expected, probably due to the limited precision of the ammeter, which introduces like small fluctuations in my calculations and measurements. And so then I moved on to constructing an RC circuit using a 9 volt battery, which can be shown right here, and then this setup allowed me to observe the time-dependent behaviors, and at one point the total current measured was 0 volts, likely because the capacitor was either fully charged or discharged, which caused the light to flicker on and off. This experiment helped me it actually helped me see how current and voltage changes over time in RC circuits. And going back to here, this is just a slide that uses all the potential differences from the circuits that I got before, and these are the results that I got or that I gained. And so going back to the linearization in RC circuits, to further analyze the behavior of the RC circuits, I used linearization. So this helped me model the exponent or the discharge of the capacitor mathematically, and so by plotting the appropriate graph, I was able to determine the time constant and confirm that the discharge followed a linear decay as shown here, aligned with a theoretical model, exponential, and I linearized the graph. And so where there's some errors, my precision relating to time may have flaws because I had to manually record the time. And so now moving on to the what if questions. What if we used a real ammeter? A real ammeter has actually some internal resistance, which slightly reduces the total current compared to an ideal ammeter. So I would expect it to go down. And then what if we used a real battery with no resistor? So without an external resistor, the model predicts an instant charging, but in real life, real batteries have internal resistance, so that's going to limit the current and cause the capacitor to charge over time anyways. Yes. Thank you so much.